All right, let's get started. So we're gonna talk about area, or I should say, we're gonna talk about estimating the area under a curve. Let's start with this first example. So let's say we want to estimate. Estimate the area under the function square root of x. Um, over the interval from 0 to 16. And we'll start using a regular partition of 4 rectangles. Regular just means they all have the same width. So regular or uniform. Let's take a look. Yeah, I can probably fit this all in here. So here's what we got going on. Our square root function looks like that. And we're going to stop here at, say, 16. So we're going to break this up into 4 equal width. Oh, you missed something? I don't see a jacket anywhere.
All right, sorry about that.
No, oh, wait, right over here.
Oh, all right.
No worries. So we're going to break this region up into 4 equal width subintervals. So the kind of straightforward to do that is to say our width, or delta x, is our b minus a divided by n, which in this case is 16 minus 0. That's our b minus a divided by 4, the number of subintervals with the number of rectangles. Happens to also equal 4, such as life. So each subinterval is going to have a width of 4. So the first one goes from 0 to 4, and then from 4 to 8, and then from 8 to 12, and then from 12 to 16. And I would say that each of these are our delta x. And I forgot to specify one thing. For this first way we're doing it, we're going to use right endpoints as sampling numbers. So for each subinterval, for this first one from 0 to 4, we're going to use the right endpoint 4 to then give us the height of the function. So we're going to say that's our height. And then our rectangle is going to have this base of 4 and this height of whatever the function value is. So that's going to be our first area. So the area approximation is going to be, well, first, the first rectangle has an area of 4 times f of 4. And the next rectangle is going to have an area of, the base is still 4, but now the height is going to be f of 8. This is going to continue. The next rectangle is going to have a base of 4, a height of f of 12. And the last one's going to have a base of 4 and a height of f of 16. So here we get 4 times f of 4 plus 4 times f of 8 plus 4 times f of 12 plus 4 times f of 16. And I think it's relatively easy to see that we can factor out the 4. So we can rewrite this as 4 times the square root of 4 plus the square root of 8 plus the square root of 12 plus the square root of 16. Which is giving us the value approximately, did I not write it down? I didn't write it down. Approximately something. Let me look real quick here. Can I figure it out real quick? I think I can, sure. Yeah, is it really that important? It kind of is. One moment while I figure this out. Yeah, no, it's not worth it. I don't care that much. It's not that important, really. We certainly could find it. You certainly could find it. But you get some value, and it certainly is, well, is it an over or an underestimate? Definitely over, right? We've got more area in our rectangles than there is under the curve. So this is an overestimate. I would also point out that in this example, for this function that is increasing, it also happens to be the upper sum, right? For each of those four subintervals, we picked the point in the subinterval that was the highest possible y value. So sometimes, not always, the right or the left endpoints correspond with the upper or lower sums. Specifically, if you have an either increasing or decreasing function, then right will be one of the things, and left will be the other thing. If it's not one of those two things, then it's a little dicier, which is why we don't usually use them. Okay, let's go the other direction. Meaning, instead of using the right endpoints, we're going to use the left endpoints. As sampling numbers. It's going to look similar-ish, but not quite the same. So now we break this up again into 4 equal subsections. Our first rectangle is kind of a non-rectangle because we're using 0 to find the height, which is going to give us a height of 0. So here's our first rectangle with a base of 4 and a height of 0. And here's our second rectangle with a base of 4 and a height of the square root of 4. Here's our third one using 8 as the sampling point. And here's our fourth one using 12 as the place where we're going to find the height. This is looking like our area is approximately, and here's the kind of shorter way of writing this. It's our delta x times our f of our first point, which is f of 0, plus f of 4, plus f of 8, plus f of 12. Almost the same as the previous one we did, except we're adding on a beginning point and we're not using the last endpoint there. But pretty similar process. Here we're going to get 4 times 0 plus the square root of 4 plus the square root of 8 plus the square root of 12. And it's certainly an underestimate. It's also the lower sum because, again, the function happens to be increasing. So all of our left endpoints happen to also be the lowest possible y value for each subinterval. Just a reminder, you're always welcome to ask questions, ask for clarification, right? It's not, I don't always want to be just me saying things, but in the beginning, it feels like there's a lot to cover. So it's often me saying a lot of things and you listening to a lot of things. But that said, if you have questions, comments, or concerns, go ahead. That's what I was about to do next. So for this example, if we use midpoints, so the thing about midpoints is there's kind of a generic formula for finding them, but really the easiest way to find them is to look at what you've got. In this particular example, I know that we're still going from 0 to 16. I'm still cutting that up into 4 subintervals. And then those subintervals have values or 0 or endpoints, I should say, 0, 4, 8, 12, and 16. And then the midpoints are going to be 2, 6, 10, and 14. So for each of these subsections, we're going to use the midpoint to find the height of the rectangle. So the first rectangle is going to have a height that's going to be the square root of 2. The second rectangle is going to have a height that's going to be the square root of 6. The third one, square root of 10. The fourth one, the square root of 14. Here our approximation would be 4 times the square root of 2 plus the square root of 6 plus the square root of 10 plus the square root of 14. Is this an overestimate or an underestimate? I don't know. It could be either, depending on how the function looks. So it's not always super clear with the midpoint rule. what you have. We couldn't really tell unless we actually found the area and then compared it to what this value was. So hard to tell if it's an over or under. I think it's a slight overestimate though, because I think this area here is a little bit more than the missing area there, but like not by a lot. Or sorry, vice versa. Apologies. No, yeah. That's what I meant to say. Yes. And then you can actually kind of use you can really use any partition you want, actually. So it's often very, very convenient to use the right endpoints to the sampling points for a number of reasons. But actually, in this example, if you wanted to kind of calculate this more easily, you could use any partition. So the partition I'm going to use now is going to be very nice. Where'd you go here? Yes. So using I didn't label that one. Yeah, I did. We're going to use a non-regular partition. So we're going to let our points be, sure. C0 is 0, C1 is 1. Yes, of course. C2 is 4. I bet you can guess what C3 is going to be. And C4 is 16. The values that are going to be easy to take the square root of. So we draw this thing out. Now I'm trying to be a little bit more precise. 16, there's 8, there's 4, there's 12. But we want different values, right? We want 1 and 4 and 9. So here are our rectangles. And now we have to be a little bit more judicious when we talk about finding the area of these rectangles, since our bases aren't all the same length. So here our area approximation is going to be 1 times the square root of 1 plus 4 minus 1 is 3 times the square root of 4 plus 9 minus 4 is 5 times the square root of 9 plus 16 minus 9 is 7 times the square root of 16, which ends up being 1 plus 3 times 2 plus 5 times 3 plus 7 times 4, which is what, 2250. Certainly an overestimate. So what are we going to do with this? Well, the idea is that we can pick any partition we want. Partition just being a way of breaking up the interval into some number, in this case 4, of subintervals. So basically between 0 and 16, we had to pick 3 points to kind of break it up at. And we did that in a multitude of ways, right? The points we picked were various. But we don't just have to use 4, right? We can use a lot more subintervals to help us estimate the area under the curve more accurately. What are we going to do with this? Well, let's look at one more thing here, just to kind of give some context. Suppose that f of t equal to the square root of t, I should move this over here so I can see it better, is the velocity of an object at time t in meters per second. What does the area under the curve represent? Well, if our horizontal axis is time in seconds, and our vertical axis is meters per second, and we're multiplying some amount of time by some amount of meters per second, we're going to end up getting a distance, right? Seconds times meters per second, the seconds are going to cancel out. So what this is representing is how much distance has been traveled if this is our velocity curve, right? If this is representing how fast we're moving at any particular time. So like at time 1, I'm moving at 1 meter per second. At time 4, I'm moving at 2 meters per second. And time 9, I'm moving at 3 meters per second, and so on. I would be covering, at least I'm estimating to be covering 50 meters altogether. So it's representing the distance traveled. And before we talk about too much more of this, we kind of have to take a detour. So we're going to come back to this idea, hopefully today. I think we have enough time. But we have to talk about the sigma notation, because what I really would like to do with this example here, if I'm writing this as something like, come back for just 1 second. If I'm writing this as something like the area is representing some delta t times f of some first value plus f of some second value plus f of some third value plus f of some fourth value. That could go on and on, but I'm just using 4 again. I really want to be able to write this in a more compact way. This gets to be very tedious for everybody. So I'd really like to be able to write this as the sum from, I like I, but we can use whatever, from I equals 1 to 4 of f of c sub I times delta t. That summation notation is very convenient and useful, but there's a few things we have to know about it to make it really work for us. So let's kind of go in that direction. We'll talk about some sigma notation, aka summation notation, and then we'll come back around to the area under the curve. So sigma notation. Also, if you have questions, I'm also not looking up a whole lot right now because I feel like I'm kind of writing fast. So you can just say, hey, James, I have a question. I'm happy to like stop and pause. So sigma notation, also called summation notation. Used to express sums. For example, the sum from I equals 1 to 5 of 6i plus 2. So here's what this says. It means we're adding up this quantity. We're starting at a value where I is equal to 1, and we're indexing up to each integer between I equals 1 all the way until we get to I equal to 5. It's kind of like a function. Yeah. No, not at all. Not at all. Imaginary numbers are not in play at all. People use I, J, or K, or M, or N typically for the index name. Your teachers has anyone's teachers gotten to this? And then what letter are they using if so? K typically, okay. K is a common choice. I can use K. See how that I becomes a K? It's magic. Cool. So all we're going to do here is we're going to sub in a value of K equal to 1 and get 6 times 1 plus 2. And then we're going to let K go to the next value, which is 2, and get 6 times 2 plus 2. You can put parentheses around this, although you don't really need to, or brackets, whatever you like, plus 6 times 3 plus 2, plus 6 times 4 plus 2, plus 6 times 5 plus 2. And that's the end because we got to the last value of K. I don't particularly care what this adds up to. What I actually care about is the way I can rewrite it. So I'll point out that I have 6 times 1 plus 6 times 2 plus 6 times 3 plus 6 times 4 plus 6 times 5. So I've got 6 times 1 plus 2 plus 3 plus 4 plus 5. I also have 2 plus 2 plus 2 plus 2 plus 2. So I have 5 times 2. Another way to write this would be 6 times the sum from I equals 1 to K equals 1 to 5 of just K plus 5 times the sum from K equals 1. Sorry, not 5 times. Apologies. That should not be there. K equals 1 to 5 of just 2. That's exactly the same thing. I'm adding up 2 5 times and getting 10, or 5 times 2. I'm adding up K, starting at 1 and ending at 5, and then multiplying each of them by 6. So what I really want us to see here is that when you have a summation of a sum of things, you can break it up into a sum of summations. Additionally, constant multiples can jump out in front. Kind of like with a derivative. Take the derivative of a constant times a function, you can pull the constant out in front of the function and just take the derivative. The same thing is true for summations. The same thing is true for integrals. So constant multiples often just get to come out in front. We could also see what this adds up to. It is going to be 6 times 15 plus 10, which I think is 100. Yeah. But that's not really the point. The point is that we can break this up. So more generally, we can say two things. Thing one, the sum of some a sub k plus b sub k from k equals 1 to wherever. It doesn't really matter where you're starting, actually. It can be written as the sum from k equals 1 to n of a sub k plus the sum from k equals 1 to n of b sub k. Or said more succinctly, you can break up a summation as a sum of summations. It also works if you have a difference. It doesn't matter if it's ak plus bk or ak minus bk. And the other thing is that constant multiples can get factored out in front. So if the sum from k equals 1 to n of some constant multiplied by a sub k, we can pull that constant out in front. You can either multiply each thing by c and add them all up, or you can add them all up first and then multiply it all by c. Same result. It's just distribution. Yeah. So let's look at one more example. Another example, I should say. It's never just one more. So another example here would be the sum from, yes. Mhm. Yeah. Totally. In fact, I wrote that in right there. So it doesn't matter if it's plus or minus. And really what's happening here that I didn't write out is that what you've got here is, sure. So right here, what you really have is on the left-hand side, the sum from k equals 1 to n of ak plus bk is going to be a1 plus b1 plus a2 plus b2 plus all the way to a sub n plus b sub n, which you could totally then break up as a1 plus a2 plus all the way to an plus b1 plus b2 plus all the way to bn. And then you could rewrite that as, oh yeah, that's the sum of the from k equals 1 to n of the a sub k's plus the sum from k equals 1 to n of the b sub k's. And if you wanted to, you could have said it was subtraction. It's a sub 1 minus b sub 1. It's a sub 2 minus b sub 2. It's a sub n minus b sub n. And then all those b's have a negative in front, so it's a minus, all those add together, and then it's a minus here. So we can always take a summation of things added or subtracted together and break it up as the subtraction or addition of those summations. It's cool. Yeah. So it's not too terrible when it's not too many things. For example, if I wanted to find the sum from k equals 1 to 4 of 3k squared minus 2k, I can write that out not too terribly. I can also break it up first and write it as 3 times the sum from k equals 1 to 4 of k squared minus 2 times the sum from k equals 1 to 4 of k. And then that's not awful. It's 3 times 1 squared plus 2 squared plus 3 squared plus 4 squared minus 2 times 1 plus 2 plus 3 plus 4, which is something. 1, 5, 14, 30. So we get 3 times 30 minus 2 times 10, which is 90 minus 20, which is 70. Which is fine until the top number gets to be like 11 or 20 or 1,000. And then you can't really, I mean, you could, but who has the time to add up all those numbers? Not me. Fortunately, there's some formulas. So if I wanted to find the sum from k equals 1 to say 1,000 of just k, which is 1 plus 2 plus 3 plus all the way to 1,000. Doesn't seem great. Yes, I can. Just to make sure I stay on camera here. So here's the trick for this. I'm going to add it to itself. So, but I'm going to write it backwards. So instead of saying 1 plus 2 plus 3 all the way, I'm going to have 1,000 plus 999 plus 998 plus all the way to 1. We're going to add these together, each side of this equal sign. On the left-hand side, I have the summation plus the summation, which is 2 of them. So it's 2 times the sum from k equals 1 to 1,000 of k. On the right-hand side, what's 1 plus 1,000? What's 2 plus 999? Also 1,001. What's 3 plus 998? Also 1,001. All the way down to the very last one, which is also 1,001. All of those are 1,001. How many 1,001s am I adding up together? 1,000 of them. So that's going to be 1,000 times 1,001. And then to get this by itself, I'm going to divide both sides by 2. So the sum from k equals 1 to 1,000 of just k, meaning 1 plus 2 plus 3 plus all the way to 1,000, is equal to 1,000 times 1,001 divided by 2. More generally, if you replace the 1,000 with the letter n, we get the formula that the sum from k equals 1 to n of k is equal to 1 plus 2 plus 3 plus all the way to n is equal to n times n plus 1 divided by 2. Just using n instead of 1,000. Yeah. Because I added the summation to itself again. So I added 1 through 1,000 plus another 1 through 1,000. So I really have 2 times 1 plus 2 plus 3 plus all the way to 1,000. So if I'm just trying to figure out what the 1 plus 2 plus 3 plus all the way to 1,000 adds up to, I have to divide this quantity by 2. It's kind of a neat trick, I think. There's other ways of doing it. People kind of like, some people do this thing where they kind of pair the ends together and do it that way. But that one is a little trickier because if you have an odd number of things, the middle thing you kind of have to worry about. But there's lots of cool ways to do it. So what I would say is there's probably a couple other formulas we need to know that are less beautiful. Sure. You guys should get to see the whole thing. So there's one more important formula, maybe 2, but one more that we'll derive. One more important formula, which requires the use of something called a telescoping sum. The reason it's called a telescoping sum is because literally like a telescope or like a spyglass on a pirate ship, it extends out way long, but then it all kind of collapses down to like the beginning thing and the end thing. Here's an example. The sum from k equals 1 to 99 of the square root of k plus 1 minus the square root of k. So if I start writing this out, let's take a look. Plug in 1, I get the square root of 2 minus the square root of 1. Plus plug in 2, I get the square root of 3 minus the square root of 2. Plus plug in 3, I get the square root of 4 minus the square root of 3. Plus all the way to the second to last term, I plug in 98. I get the square root of 99 minus the square root of 98. Plus the last time I plug in 99, I get the square root of 100 minus the square root of 99. But a lot of things are going to cancel. The square root of 2 and the negative square root of 2. The square root of 3 and the, oh, that should be a negative there. Sorry about that. The square root of 3 and the negative square root of 3. The square root of 4 and the negative square root of 4 that would have been in the next term that I didn't write. All the way to the square root of 98 there and the negative square root of 98 there. The square root of 99 there and the negative square root of 99 there. So it flattens down or compresses down just to the first term and the last term essentially. So I end up getting the negative square root of 1 plus the square root of 100, which is negative 1 plus 10, which is 9. It's kind of cool. This idea definitely is going to come back in 21C when we talk about series in more depth. Yeah. So we're going to use this idea to find a formula for the sum from k equals 1 to n of k squared, which is 1 squared plus 2 squared plus 3 squared plus 4 squared all the way to some n squared. What's kind of neat is you can actually do this for any positive integer power. You just have to know all the ones before it. So yeah, it's a bit of build up every time, but it is kind of a neat process. It's kind of a terrible pain in the butt, but it's kind of neat. Do I have enough room here? It's always a question. We'll start here. We might need another page. So we're going to start with the following. The sum from k equals 1 to n of k plus 1 cubed minus k cubed. Whatever thing you're trying to find the formula for, you do the telescoping sum of the next highest power. So if I was trying to do the formula for like the sum of the cubic numbers, I would start with the sum of k plus 1 to the fourth minus k to the fourth. We're going to do this in two different ways. We're just going to write it out in the first place. So we start writing things out. I get 2 cubed minus 1 cubed plus 3 cubed minus 2 cubed plus all the way to this. I always like to write the second to last term. I find it helpful. So I'm going to plug in n minus 1. n minus 1 plus 1 is n minus n minus 1 cubed. And then finally, the very last term, when I plug in n, I'm going to get n plus 1 cubed minus n cubed. Cancel some things. The 2 cubed with the negative 2 cubed, the 3 cubed with the thing that comes after it, the n minus 1 cubed with the negative n minus 1 cubed there, the n cubed with the negative n cubed there, and we're left with negative 1 cubed, which is just negative 1, plus n plus 1 to the third power. Let's simplify that. That's negative 1 plus n cubed plus 3n squared plus 3n plus 1, and the negative 1 and the 1 cancel. So we've got this. Okay. The other way we're going to do this is by breaking it up using the rules of summations. We just talked about how you can break up a difference into the difference of sums and so on and so forth. So we're going to do this like this. Yeah. So first multiply it out. So the k plus 1 cubed is going to become k cubed plus 3k squared plus 3k plus 1 minus k cubed. The k cubes cancel. We're going to break this up into 3 summations, and we're going to pull out the constant multiples. So we're going to rewrite this as 3 times the sum from k equals 1 to n of k squared plus 3 times the sum from k equals 1 to n of k plus the sum from k equals 1 to n of 1. This is what we're trying to find. We know everything else. So here's what we've got. We've got 3 times the thing we're trying to find plus 3 times the sum from k equals 1 to n of k. We just showed what that formula was equal to. It's n times n plus 1 divided by 2. Plus the sum from k equals 1 to n of 1 is 1 plus 1 plus 1 plus 1 plus 1 n times. That's going to be n. And that should be equal to the other way we found it, which was this quantity here. N cubed plus 3n squared plus 3n. Well, that looks terrible. Let's make it a little bit easier. I would say, let's bring all this stuff to the other side, and also let's multiply both sides by 2. Let's do that first, actually. So multiply both sides by 2, I've got the following. 6 times the sum from k equals 1 to n of k squared, plus, if I multiply this by 2, the 2 is going to cancel. I'm going to get 3 times n plus 1, plus 2 times n equals 2n cubed plus 6n squared plus 6n. Just so I don't have to deal with fractions. Subtract this stuff over. So 6 times the sum from k equals 1 to n of k squared is equal to 2n cubed plus 6n squared plus 6n minus 2n. And this multiplies out to 3n squared plus 3n. So we're subtracting 3n squared minus 3n. Simplifying, we get a 2n cubed. We get a 6n squared minus a 3n squared, which is a 3n squared. And we get a 6n minus 2n minus 3n, which is an n. Finally, 2 steps in one go. Divide both sides by 6. So you get 2n cubed plus 3n squared plus n divided by 6. And then we usually write the numerator as the factored form, n times n plus 1 times 2n plus 1 divided by 6. It's kind of a lot. I would probably recommend memorizing this formula. It does come up often enough that you probably want to just know it. So here's what we've got as far as these formulas go. The sum from k equals 1 to n of k, we just did before. It's n times n plus 1 divided by 2. The one we just did, the sum from k equals 1 to n of k squared, is 1 squared plus 2 squared plus 3 squared plus all the way to n squared, which is n times n plus 1 times 2n plus 1 divided by 6, which kind of makes you feel like it's going to be like a pattern. Like you're like, oh, the next one's going to be like n times n plus 1 times 2n plus 1 times 3n plus 1 divided by, I don't know, like 24 or something. It's not. I wished it was, but it's not. The next one is really cool, though. I mean, for math. Okay, so the sum of the cubes, 1 cubed plus 2 cubed plus 3 cubed plus all the way to n cubed, is n times n plus 1 over 2. Oh, that looks familiar. Squared. That might not seem interesting at first, but let me show you what I mean when I think it. I think this is a really cool fact about math. So if you take, say, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, which is equal to 1 plus 8 plus 27 plus 64, which is equal to 100. It's equal to 1 plus 2 plus 3 plus 4 squared. I just think that's super neat. That if you add up the first n cubes, it's the same as adding up the first n numbers and then squaring the result. Impress your friends. They might not be impressed. All right, so let's see, what else have we got here? Sure, so back to the question we asked. Oh, no, we didn't ask that question before. Yeah. So then you can use these formulas to like calculate things. Not that we really do a whole lot of that, but for instance, we could say, what's the sum from k equals 1 to 10 of k cubed plus 4k squared minus 2k? And then you can just throw formulas at it. So actually, I should say, before we can throw formulas at it, we have to break it up into things we can use. So I really want to break this up as, say, like the sum from k equals 1 to 10 of k cubed plus 4 times the sum from k equals 1 to 10 of k squared minus 2 times the sum from k equals 1 to 10 of k. And then I would use the formulas. Okay, for k cubed, I know it's n times n plus 1 times 2n plus 1 divided by 6. And in this case, my n is equal to 10. That's going to be 10 times 10 plus 1 times 10 times 2 times 10 plus 1 divided by 6 plus 4 times, oops, that's the wrong formula, James. I was using the k squared one. Boo, let's try that again. So for k cubed, it's the n times n plus 1 divided by 2 quantity squared. So that's going to be 10 times 10 plus 1 divided by 2 quantity squared plus 4 times, for k squared, it's the n times n plus 1 times 2n plus 1 divided by 6 minus 2 times the sum of k is n times n plus 1 divided by 2. And then we could simplify that. We've got 5 times 11 squared plus 4 times this 10 times 11 times 21 divided by 6 minus 10 times 11. It's a number. It's 55 squared. I don't know. Plus 55 times 7. There's a lot of 55s over here. Minus 110. Whatever that happens to be. But the point is, we could find these things. And that's what we're going to do to help us actually calculate the area under the curve of some functions. So believe it or not, we're about to use this to find the area under a curve. I mean, I'll be honest, when I took 21B at UC Davis too long ago to mention, we did have to do it on an exam, but that was many years ago. So I don't know if they still make you do that on an exam. I think it was an extra credit question. I'll go look. I still have my exams. I'll check it out. But it's possible, right? You could be asked to derive that. I've certainly seen people ask students to do it either in discussion sections or homework problems to like derive the formula for the sum of the first 10 cubes. It's doable. We just did it. Or no, we did the squares. You can do so I'll say to do the cube ones. So if you wanted to, we wanted to derive the sum of k equals 1 to n of k cubed equal to the thing we just found it to be equal to, you would start with the next highest power, the telescoping sum from k equals 1 to n of k plus 1 to the fourth minus k to the fourth. And then calculate it in the two different ways by writing out the telescoping thing and then just seeing it's like the end thing minus the beginning thing. And then also by multiplying this out, subtracting k to the fourth, breaking it up into 4 pieces, and then getting the one left and using the other ones now. Quick check here. So I'm curious if I was going to find k plus 1 to the third. I did that really fast when we were doing that, right? I was just like, it's k cubed plus 3k squared plus 3k plus 1. There is a trick that I'm using. I'm using not Pythagorean, the Pascal's triangle. So, right, for k plus 1 to the fourth, what I'm really doing is I'm being, oh yeah, for Pascal's triangle, it's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So for k plus 1 to the fourth, it's 1 times k to the fourth plus 4 times k to the third plus 6 times k squared plus 4 times k to the first plus 1 times k to the 0th. That's how we're doing that. So if you ever have to do that fast, Pascal's triangle gives you the coefficients there. It's nice. It's a cool trick. All right. Plenty of time. Not really. So, yeah. Go back this way. So for our previous example of f of x equal to the square root of x on the interval from 0 to 16, using right endpoints, our approximation was the following. And I guess I can draw the picture again. Sure. I've drawn it like 10 times. But I want to be kind of extra specific with my notation here. So we're really calling each of these endpoints our C value. So this is our C0, our C1, our C2, our C3, and our C4. And we're saying that the area is approximated by the sum from k equal to 1 to 4 of the function evaluated at whichever point we want to use. In this case, we're using C sub k, the right endpoint, times our delta x, the width of our rectangle. So I'll point out, this is the height of the rectangle. This is the width of the rectangle. And the area you get by multiplying them together. And then we're adding up all the areas of the rectangles to get an approximation of the total area. And then we did this before, but again, so this is just going to be f of c sub 1 times c sub 1 minus c sub 0 plus f of c sub 2 times c sub 2 minus c sub 1 plus f of c sub 3 times c sub 3 minus c sub 2 plus finally f of c sub 4 times c sub 4 minus c sub 3. Which in this case happens to end up being the square root of 4 times 4 plus the square root of 8 times 4 plus the square root of 12 times 4 plus the square root of 16 times 4, which is approximately 49.2. How do we get a better approximation? More rectangles. Okay. So instead of drawing more terrible pictures, let me just show you a useful tool. So this is linked in our canvas here. Sorry, I'm covering things up, but more rectangles. You all can see that, right? More. Okay. So this is the Riemann sum tool that I've linked in our canvas, which I think is super useful. And it kind of shows you all the things. So if we were graphing, say, the square root of x, you can then, we'll turn this off for a second. So you can kind of do whatever you want. So these blue dots represent like your beginning, your end place. So I want to start at 0, and I'm going to zoom out. I'm going to end at 16. Oh, too far out. Makes you can grab it that way too. And then I can either use, if I click on the relative thing here, you can slide it from left to right. So there's my right endpoints. And if I bring this back over to 4, it's very kind of very responsive. So therefore, n equal to 4, using right endpoints, I'm getting approximately 49.17 or 49.2, as I said earlier. And then you can also just shift this way over to the left to get your left endpoints. Beautiful. You can also, it'll also stop right in the middle if you want. For the midpoints. Kind of cool. Tells you what so the red number here is what the approximate value of your estimate is. And then you can also, although it's not going to be super different here, you can do the upper sum, which in this case is also the right endpoints, because it's an increasing function. It's the biggest to the right. Or you could do the lower sum using the left endpoints. Kind of great. Not that this is a replacement for doing it by hand, well, I mean, kind of is. But it's just, you can see things much more quickly. And then if you want to, say, use right endpoints, maybe if I can grab the thing there, you can then say, well, what if I wanted to use 17 rectangles? 17 seems like a terrible number to use. 16 rectangles. Oh, look, our estimate got better. Now our estimate is 44.46 or 47 instead of 49.2. And if you go real big, your estimate gets to be very, very close to the actual value. So our estimate here is 42.97. The actual value of the area under this curve is 42.666 forever, or 42 2/3, which we will calculate eventually, maybe today. So that's kind of the idea, is we're going to let the number of rectangles get larger and larger and larger. Another way of phrasing this, which I haven't really talked about too much, is we're going to let the partition get smaller and smaller. No, not the norm of the partition, sorry. So I don't really talk about that a whole lot because it's annoying, to be perfectly honest, but I probably should. So you can either talk about finding the actual area under the curve by letting n the number of rectangles go to infinity. Or equivalently, we can let the norm of the partition. So what am I even saying? Go to 0. So the partition, for example, one of our partitions of 0 to 16, one of our partitions of the interval from 0 to 16. Well, let's actually, well, two of them. Two of our partitions were, one of them was 0, 4, 6, 12, 16. And another one, which was kind of more interesting, was 0, 1, 3, sorry, not 3, 4, 9, 16. Both of these broke up the interval into 4 subintervals, right? Using 5 endpoints. You need 5 endpoints to get 4 subintervals. Here, the norm of the partition is equal to 4. It's the length of the longest subinterval. And I guess I should be using some, like, this is like, I really hate this. I'm sorry. I'm doing the not best job here because I don't do it very often because I always do it the other way. So I apologize for not being the best about this. So our partition is this. The norm of our partition is 4. Over here, our partition is 0, 1, 4, 9, 16. And what's the biggest length between any 2 points? 7. So here the norm of our partition would be 7. But the idea is, if we let this norm go to 0, that's the same as letting the number of partitions get larger and larger and larger. Because for the distance between any 2 partitions to get smaller and smaller and smaller, we have to have an infinite number of partitions. That's kind of the idea. The norm of the partition going to 0, or the number of partitions, the number of subintervals getting super large, ends up being the same in the end. This is a little bit more general though, because it's really, really nice when our partition has all equal length subintervals. That's what we would love to have every time, but sometimes we don't. So we have to be more general with this norm of the partition notation. Well, I don't have to be. You have to be. Yeah. So let's look at you mean like this?
Yeah.
It's just different notation. Some people use more of an absolute value notation. Some people use the double absolute value notation, which is for the length of something in it's really either way. It's a personal preference, I guess. So what we're going to do with this is say we can find the area under some function f of x over some interval from a to b by estimating the area using n rectangles of equal width. At least that's the way we're going to prefer to do it. And then by taking the limit as n goes to infinity. So I like to draw a picture here. I find it helpful. Maybe. Can you stay? Sure. Okay. Well, I want to find the area under this curve. The idea is that we're going to look at an arbitrary subinterval here. So let me make sure I'm using, yeah. So I'm thinking of this leftmost point as my C sub 0. And then the next one is going to be C sub 1, and then C sub 2, all the way to some C sub k, C sub k plus 1 all the way to some C sub n. No. And I guess I wanted, I meant to get one more over here, sorry. Before that, C sub k minus 1. That looks really small. I can zoom in more. Kind of nice to be able to zoom more. So we're going to write down the area using right endpoints. So I should say we're going to estimate area under f of x using n subintervals or n rectangles with right endpoints as our sampling points. Okay, so very broadly, our width of each rectangle, our delta x is going to be b minus a divided by n. And our sampling points are going to be the right endpoints. So our area is going to look like f of c sub 1 times delta x plus f of c sub 2 times delta x plus all the way to f of c sub n times delta x, or written using our summation notation, the sum from k equals 1 to n of f of c sub k times delta x. I'll point out that if we were to use left endpoints as sampling points instead of right endpoints, the only thing that would change, well, one of the ways you could change it, we'd write this as c sub k minus 1. So this is with right endpoints. And if it was for some reason convenient, you could write it as the sum from k equals 1 to n of f of c sub k minus 1 times delta x if you wanted to use left endpoints. Yes, am I off screen? Thanks. The problem with zooming in so much, easy to get off screen. So I will point out, looking at my notes here, there is a reason we say the partition has to go to 0 instead of just saying n has to go to infinity, because you could have one really wide rectangle that never got smaller and smaller if you just had the number of rectangles that they get larger and larger and larger. So this is a special case. I will point out that more generally, we could actually, I'll say that on the next page here. Sorry, we're almost there. Apologies. So here's what we're going to say. I would like to write it on this page, I think. Let me zoom out a little bit. So the area under the curve which we're going to represent as the integral from a to b of f of x dx. It's the area under the curve. It's just notation for it. Has no other meaning yet. We can say this is equal to the limit as n goes to infinity of the sum from k equals 1 to n of f of c sub k times delta x. Or we can also say it's going to be the integral from a to b of f of x dx is equal to the limit as the norm of the partition goes to 0 of the sum from k equals 1 to n of f of c sub k. And then instead of writing just delta x here, delta x is making the assumption that all partitions have the same width. We'll actually just write it down as c sub k minus c sub k minus 1. Right? Each partition's width is just the right endpoint of that partition of that subinterval minus left endpoint of that subinterval. And if we're saying this width has to get smaller and smaller and smaller, then we're saying the number of rectangles has to get larger and larger and larger. But in practice, this is the way we almost always do it. Really in practice, again, like I was saying on Tuesday, just like we learned the limit definition of the derivative and then we almost never used it after we learned other ways to do it, same kind of idea here. We're learning this thing because that's how it's built up, but then we're going to learn much easier ways of actually calculating area under curve without using all of this machinery.
Can you explain what you use on the rectangles that it's getting bigger? Can you explain
What the what means? So what we're talking about here is we're saying this formula specifically is, we're adding up the area of all the rectangles. And this n here, we're just saying we're letting the number of rectangles get larger and larger and larger. So all of their widths are going to get smaller and smaller and smaller. And our estimate is going to approach the actual value of the area under the curve. And then I was kind of saying over here, another way of saying that is instead of saying really the number of rectangles get larger, we're saying that the norm of the partition, which is just the longest length of any of the subintervals, that longest length has to get smaller and smaller and smaller. But most people don't do it that way in practice. So, how much time have we got? Yeah, we got enough time. Okay. Right, that clock is right? Yes, that clock is right. Cool. So now we will actually find the area under a curve. Yeah, we'll do that one. Sure. It's kind of a lot, so strap in. I mean, I know it has, so far it's been fine, right? It's been a lot already, but it's about to be very calculation intensive. So we're going to calculate the area under f of x equal to, sure, we can use that. I'll change it up a little bit. 3x plus 2 on the interval from 0 to 2. In other words, find the area under 3x plus 2 over this interval from 0 to 2. Oh, sorry, let me scoot down just a little bit here. So we don't have to draw a picture here, but I kind of like to. My function is y equals 3x plus 2. It looks vaguely like this. I don't actually really care what it looks like as long as it's close to being right. I'm going from 0 to 2. So I'm looking for this area here. And I'm going to use n rectangles. So first of all, if I'm using n rectangles, then my delta x is going to be b minus a divided by n, which is 2 minus 0 divided by n, which is 2 over n. It's as simple as it gets. And then my endpoint of each subinterval, well, my left endpoint is a equal to 0, which is also my c sub 0. Always my starting place. And then the next one's going to be c sub 1. And the distance from c sub 0 to c sub 1 is my delta x. So this little distance right here is delta x. So my c sub 1 value is, well, it's delta x, right? It's 0 plus delta x, which is just 2 over n. And my c sub 2 value is just another delta x away. So c sub 2 is 0 plus 2 times delta x, which is 2 times 2 over n. And my c sub 3 is going to be 0 plus 3 times delta x, which is 3 times 2 over n. And it looks like my c sub k is going to be k times delta x, which is k times 2 over n. Generally, your c sub k is equal to a plus k times delta x. Your starting place, a, which is 0 in this case, plus however many delta x's you have to go over to get to that subinterval. You're just adding the width that many times to get to that spot. Okay. Also, a nice check on this, I think, is that if you plug in 0, you should get your A value. If you plug in n, you should get your B value. So if I plug in A equal to 0, C sub 0 is equal to 0 times 2 over n, which is 0. If I plug in n, C sub n is equal to n times 2 over n, which is 2. Checks out. My starting place is 0. My ending place is 2, which is my B value, which is my C sub n value. Okay, so now we're going to write it all down. I'm sure I'll write it here. My integral from 0 to 2 of 3x plus 2 dx, again, just meaning the area under the curve, is going to be the limit as n goes to infinity of the sum from k equals 1 to n of the base, which is delta x, which is 2 over n, times the height, which is f of delta x. Sorry, f of c sub k. So it's my f of c sub k times my delta x, which in this case is going to be f of c sub k. My function is 3x plus 2, so it's going to be 3 times my c sub k, which is, I'm going to write that as 2k over n plus 2, all times my delta x, which is 2 over n. That's what we're going to have to calculate. It's not too terrible. Here we go. Make sure we can see all the things. Okay, so the limit as n goes to infinity of the sum from k equals 1 to n of 3 times 2k over n plus 2 times 2 over n. We want to simplify the insides of the summation first. So 3 times 2k over n is 6k over n plus 2, all multiplied by 2 over n. That's going to equal the limit as n goes to infinity of the sum from k equals 1 to n. 6k over n times 2 over n is 12k over n squared, plus 2 times 2 over n is 4 over n. And now that we've simplified the inside as much as possible by kind of multiplying it all out, we're going to break this apart into however many summations we need and factor out the constants. I will point out here, from experience, I know we're in a good spot because the power of k is 1 less than the power of n, or the power of n is 1 greater than the power of k in each fraction. I've got n squared, I've got k to the first, I've got n to the first, I've got k to the 0th. I'm happy about that. That means we're going to be good. So then we're going to break this apart as the limit as n goes to infinity of, we're going to have two sums. My first sum is going to be 12 over n squared times the sum from k equals 1 to n of k plus 4 over n times the sum from k equals 1 to n of 1. Anything that isn't k is a constant as far as that summation is concerned, including n. N's not changing yet, right? We haven't taken the limit yet. We're just letting n do its thing here, and then we're eventually going to take the limit. But n could be 100 or 1,000, whatever, but it is a constant as far as the summation is concerned. In the summation, k is the only thing that's changing. So k is the only thing that has to stay inside the summation. And now we're going to use those formulas we spent time figuring out what they were. We're going to get the limit still. We still haven't taken the limit, so we still have to write it. As n goes to infinity of 12 over n squared times the sum from k equals 1 to n of k is n times n plus 1 over 2 plus 4 over n times the sum from k equals 1 to n of 1 is n. We're almost there. I would generally recommend not multiplying off the top, especially if it's more complicated. This one's probably fine to multiply out, but in general, you don't have to multiply out. Just have to see what's going to happen. But let's see what happens if we do multiply it out. The limit as n goes to infinity of, on the bottom we have 2n squared. On the top we have 12 times n squared plus n, which is 12n squared plus 12n. Over here, 4 over n times n is just 4. Okay. What's the limit as n goes to infinity of 12n squared plus 12n over 2n squared? 6. right? It's that situation where, oh yeah, we're taking the limit as something goes to infinity, and it's a rational function, and the degree on top and the degree on the bottom are the same. So the limit's the quotient of the leading coefficients. It's just like how the limit as x goes to infinity of 3x squared plus 5x plus 7 over 8x squared minus 9x plus 2 is equal to 3 over 8. Because you have the same highest degree on top and bottom, and so the limit's just the fraction of those coefficients. So here we're going to get 12 over 2 plus 4, which is 10. Which might be true. In this case, we can show it's true because the region we're finding the area of is geometrically easy to compute. So we look back at the region we were talking about. It looked vaguely like this. The function was y equal to, what was it, 3x plus 2? I think so. What did I write down earlier? Yep, 3x plus 2. And we're going from 0 to 2. Well, that's not too terrible. That's just a rectangle and a triangle. We can find the area of a rectangle and a triangle. The rectangle has a base of 2 and a height of, well, if we plug in 0 to this function, 0 plus 2 is also 2. And then the triangle has a base of 2 and a height of, we plug in 2 here, we get 6 plus 2, which is 8. 8 minus 2 is 6. So the area is going to be the area of the triangle, which is, sorry, the area of the rectangle, which is 2 times 2, plus the area of the triangle, which is 1/2 times 2 times 6, which is looking a lot like 4 plus 6, which is 10. So we can see, in fact, that the area actually is 10, and they calculated it this way, it didn't lead us astray. So then you might ask, well, why would you do it for this one when you could just do it that way? Well, because we wanted to show that it was true. But then we can use this to find the area under curves that are not easy to compute, like things that are actually curvy. Like, for example, yeah. Ooh, okay, 8 minutes, we can do it. Sure. Like, for example, we want to evaluate the integral from, yeah, we'll still keep it not too terrible, from 0 to 3 of x squared plus 5x. Yes, yes, yes. Using the limit definition of the area and right endpoints. Okay, so here we go again. We're going to start by writing this as, so normally I wouldn't draw the picture that I drew last time. Like normally I would just say, okay, I know that this is going to end up equaling limit as n goes to infinity of the sum from k equals 1 to n of f of x sub, or sorry, c sub k. So our f of c sub k is going to go right there, times our delta x is going to go right there. That's always what's going to be in there. It's always the height times the base. Our base we want to find first, our delta x is equal to 3 minus 0 divided by n, which is 3 over n. Our c sub k is a plus k times delta x. That's going to be 0 plus k times 3 over n, or 3k over n. And then we jam that into the function. The function is x squared plus 5x. So our f of c sub k is going to be 3k over n squared plus, that's an x, James, 5 times 3k over n. That's what we're starting with. The process is the same as before, just more terrible. We multiply it all out. So I'll say it's extra terrible when one of your endpoints isn't 0. Because if it wasn't 0, instead of having a 3k over n, we'd have like a 1 plus 3k over n quantity squared, and a 1 plus 3k over n times 5, which just makes it even worse. We'll do some of those next time. So here we have the limit as n goes to infinity of the sum from k equals 1 to n. We're going to have 9k squared over n squared plus 15k over n, all times 3 over n, which then is going to be the limit as n goes to infinity of the sum. We see that a lot. 9 times 3 is 27 n, sorry, k squared over n cubed plus 45k over n squared. Again, I'm happy about where I'm at because my powers of n are 1 larger than my powers of k. This is always what I'm hoping will happen here. As long as it's a polynomial. If it's something else, it's much more complicated. So then we break it apart. I'll show the intermediate step here. So here's one of the 2 steps, breaking it up as k equals 1 to n of 27k squared over n cubed plus the sum from k equals 1 to n of 45k over n squared. And then we're going to bring out the constants. We're going to pull out the 27 over n cubed of the sum from k equals 1 to n of k squared, and pull out the 45 over n squared. We have the sum from k equals 1 to n of k. And we do that so that then we can use the formulas that we found. We know what the first n squares add up to. We know what the first n numbers add up to. So this is going to equal the limit as n goes to infinity of 27 over n cubed times n plus 1 times 2n plus 1 divided by 6 plus 45 over n squared times n plus 1 divided by 2. And here is what I mean by you don't have to multiply these out. All you have to be able to do is recognize for each of the separate things what the leading term is in the numerator and the denominator. So for this first part here, the leading term in the denominator is obviously 6. I get a 6n cubed in the bottom. In the numerator, I would get an n times 2n times 27, which is going to be a 2 times 27 as my leading coefficient. Yes, it's 54, but I don't really actually need to multiply it out because I'm going to divide by 6 anyway. Over here, 45 times n squared over 2 times n squared. The leading coefficients are the only thing that matters in this type of problem. So we end up getting, let's see, 9 plus 45 over 2. I guess I could have left that as 18 over 2 plus 45 over 2, which is 63 over 2. Or if you prefer, 31.5. And it is. That is the actual area under this curve. We can even go look at the other thing. Maybe. We'll see. If I can see it. Our function was x squared plus 5x. We went from 0 to 3. Let's zoom in. Oh, gosh. Can I zoom in a bit? Zooming on this thing is kind of funky, I gotta say. Can I? Nope. Stuck. Sorry. Wow. I've blown it here. Pull it back over a little bit more. Maybe. Okay, this thing is usually pretty good. It's kind of hard to do over here, though. Go right to 3. And the area is 31.5, just as promised. So it does work. It's just tedious. So obviously, we will learn better methods of finding area under curve. But for now, the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum from k plus 1 to n of f of c sub k times delta x. That is our area under the curve. That is our integral definition for now. Or one of them, I should say.